R of T is the amount of sand that is being removed from the beach from the tide. S of T is the amount of sand that we're going to pump back into the beach. Part A is just asking how much sand will the tide remove. So that's strictly just talking about R of T. And your integral is an accumulator. So if you want to add up all 6 hours for you, what we're going to do for part A is we're simply going to integrate between 0 and 6 of that R of T. So you're allowed to write it just like that. You don't have to write down the whole function, or you can write down the whole function if you want to, but math 9 that thing right there, and then I'll get you your answer. And you're around the 3 numbers after the decimal. It does ask us to indicate units of measure. So it's talking about how much sand, and it also tells you the units on there are cubic yards. So when you integrate that cubic yards per hour, you're going to get just cubic yards, and that's how much sand is left right there. So there's part A. This is kind of a really important problem. You're going to see a lot more of these in the future. It's like our first time seeing stuff like this. So probably had a lot of questions on this one. Now, what we got to take into account on part B, it says write an expression for the total number of cubic yards of the sand at time T. When you see this total amount type of problems, you'll see this concept a lot. We got to take into account always 3 things. We got to take into account how much was already there, which it tells us we're starting with 2,500 cubic yards of sand on the beach. Then you got to add in how much we pumped in. Then you got to take out how much was removed by the actual water. So you got to remember that initial amount. So for part B, this is what we got going on right here. I took into account the initial amount was the 2,500. Now, when you integrate the S, that'll add up in the T hours, how much sand was added to the beach. When you integrate the R, that'll add up how much sand was left from the beach. And so we subtract that one because that's being removed from the beach, and you add this one in, this is positive, because that's how much sand is being added into the beach there. So keep that in mind. We'll refer to this sand problem on future problems where you got to take into account the initial amount plus what we added in minus what we're going to take out right there. So that's what they're talking about on part B. Letter C is just saying find the rate at which that total amount of sand beach is changing. When you see rate changing, we know that's the key word for derivative. And so it says the total amount of sand. So they want us to go back to part B. This is our total amount of sand equation. We're supposed to take the derivative of this at T equals 4. Now, just as a little sidebar, when we do the derivative of the integral, that just, it's like square root and something squared to there. You're going to get your original function back again. So when I take the derivative of that, that's 0. And then the derivative of an integral is going to be just that original inside function right there, right? So there's like our derivative equation. And it says at T equals 4. So your derivative is equal to simply S minus R. And they gave us both of those equations right there. I have the S equation and the R equation. So all you got to do is plug in the 4. S of 4 minus R of 4. Plug the 4 into both of those functions. Let that calculator do the work for you. And that's how fast that's changing. So that's going to be the cubic yards per hour right there. Letter D is, it gives you a closed interval, and when is the amount of sand on the beach a minimum. Anytime you see a maximum minimum problem and it gives you a closed interval, what they're meaning for us to do is a 3.1 absolute extrema problem. So if you look at your blue packet, your calculus summary packet, absolute extrema, 3.1 absolute extrema problem is when you got to make a normal XY chart, and on that XY chart, you got to check the endpoints of your interval and your critical numbers, right? So try to take advantage of this blue sheet. It reminds you of a lot of important processes that we want to make sure we get down, okay? So for letter D, when it says minimum, I'm going to first take the derivative and then set that equal to 0 to obtain the critical numbers. Now down here, I'm going to make an XY chart or a TY chart. I'm going to check the endpoints of my interval and the critical numbers that we get right there. So that's what I'm trying to do. But so I already know I'm going to check the endpoints there. Let's get the critical numbers. So again, we're going to take that derivative. We already set up there in letter C. That's what my derivative was equal to for that total amount of sand. And we need to set this equal to 0. Now, this is a very difficult equation to solve without the calculator. You're not meant to solve that without the calculator. I show how to do this exact problem in the graphing calculator video. So if you haven't watched that yet, go ahead and do so. If you already watched that, try this on your own where you graph it in your calculator, let it calculate the zero for you to get that 5.118 number. Then once you get that, that doesn't mean that's where your max or min is going to be at. It could also be at the endpoints if you check your 3.1 notes on it. So what we're going to do here is just we got to take all three of these numbers, plug those into the y of t equation. That's going all the way back up to this guy in part B. I got to plug in those numbers for this t right here, right? Between 0 and 6 hours, between 0 and 5.118 hours. And then there you can use your alpha trace shortcuts in order to help you with that stuff as well. Now, we already know at 0, they told us that was 2,500. And then instead of plugging all this into the calculator, we showed you kind of how to access those alpha trace shortcuts from your Y1 and your Y2 from your calculator. So if I show you how to plug this in, notice I already have that function graphed in the calculator. That's this whole entire thing. That's like my y of t right there, okay? And this is what we showed you in that video, how to find that 0. Now, when I do this problem, I'm gonna do the 2,500 plus, then I'm gonna hit the math 9, go from 0 to 6. You know, the old software, we used to have to type all of that stuff in. It would just take forever. And now that's already in my calculator. So all I gotta do then is hit that alpha trace, access that Y1. Now, if it wasn't already in your calculator, then I just type it in. You got to type it in at some point anyways. And I hit that variable button right there. And then see, that's going to give us the total amount of sand on the beach. It's taking a little while on this one. There's that 2493 number that we got right there. And then also, you could just go up in there now, hit enter on that, and then just simply change that 6 to the 5.118. Math 9 that thing, and then it gives you the total amount of sand on the beach right there. And this one says what's the absolute minimum, what's the lowest amount of sand. So if it says where does the maximum occur at, that's your t value. If it says what is the minimum amount of sand on the beach, that's the number of cubic yards of sand on that beach right there. This particular problem asks us for both. It says what time is the amount of sand minimum, and what is that minimum value. So they want the x value and the y value. Sometimes they'll just ask for one, but there's a lot of neat work for that and a little explanation for that. And then, like I said, if you get stuck with the calculator stuff, watch that graphing calculator video and please practice these things on your own. Pizza rolls.